Okay, so when we last left off, we discussed the model of electrons as having both wave and particle properties. Now we're going to look in a little more, we're going to look into the quantum model in a little more detail and start to look at how we can model electrons as waves. So, critical to this idea of the quantum model of an electron is this idea of wave-particle duality. So electrons exhibit both wave and particle properties depending on the experiment performed. In general, subatomic particles exhibit both wave and particle properties. So wave and particle properties are known as what are called complementary properties. And these are properties that cannot be simultaneously determined beyond a minimum amount of uncertainty. So rather than seeing simultaneously wave and particle properties, we instead, depending on our experiment, will observe either wave or particle properties. And this is due to the fact that experiments to observe one complementary property inherently preclude observation of the other complementary property with a high level of certainty. In other words, you cannot measure both complementary properties at once. Now, the Heisenberg uncertainty principle essentially described a relationship and provided a mathematical model that conveys this idea that we can't simultaneously observe the wave and particle properties of electrons simultaneously. So this delta x is the uncertainty in the particle's position, m is the particle's mass, and delta v is the uncertainty in the particle's speed or velocity. In essence, what this uncertainty principle is stating is that we cannot simultaneously measure an electron's position and energy. Okay? So we can measure one or the other. So to delve into this uncertainty principle in more detail, it essentially is stating that the position, which is a descriptor of the particle nature, and the velocity, which is a description of the wave nature of a particle, are complementary. We cannot simultaneously measure the position and velocity of a particle with certainty. Now, because the energy of a particle is dependent on the velocity of the particle, one way that we can rewrite the uncertainty principle is that the position and energy of a particle are complementary, and it is impossible to determine the position and energy of an electron simultaneously. Now, why is this important? Well, chemical reactions are governed by the position and energy of electrons. So we're interested in models fundamentally to understand the relative location of an electron for a given energy. However, if we had to pick one of these two complementary properties to determine with a high degree of certainty, we are far more interested in the energy of an electron. So we will concede a little bit of certainty in the electron's position. So what we're going to do, and this is in essence the key takeaway from this quantum model, we can't fully determine the energy and position of an electron simultaneously. So what we're going to do is, for a specific electron energy, we're going to describe the electron position as a probability distribution. We're going to say for a given energy, the electron is likely to be in a location. There's an inherent uncertainty to the electron's position, but we will be able to clearly define the electron's energy. So, an orbital is a construct that we use to describe the probability density for the location of an electron for a given energy. Okay, so what this orbital depiction is saying, what this orbital depiction is trying to convey is that in this region of space, an electron has electron of a given energy has a probability of being present in that space. One way to think about it is if you've ever, for example, ordered an Uber or another ride-sharing service, you sometimes see this little indicator where the driver is somewhere in this region of space. So the driver is likely to be somewhere in this region of space. You have an idea, just like with your electron, you have an idea that of the electron's energy of the drive, how fast the driver is going, but you don't know the exact location. You only know they're likely to be in a certain region of space. So we are describing an electron's location as a probability density. The electron is likely to be in this location if that electron has a specific energy. Does this idea make sense to everyone? We've given up some certainty in the position of an electron so that we can more accurately model and describe the energy of an electron. Can I get some responses in the chat just to make sure everyone's comfortable with this idea? Does this make sense so far, what we're doing in this quantum model? Okay, so let's delve into a little bit the Schrodinger model, and let's talk a little bit about how it works. We aren't going to be going through and doing the full derivation, as that requires a little bit more math than we currently have as prerequisites for this class, but we'll walk through qualitatively what's going on in the Schrodinger model and what each of these parameters mean. So first, let's discuss our goal. And our goal is to estimate values for the energy of an electron. And this wave function symbol, quite simply, is a function that models the energy of an electron as a function of different quantum numbers and other parameters. This wave function is describing the wave nature of an electron. Now, when you solve the Schrodinger equation, you will get a series of wave functions. Now, this wave function doesn't have any inherent meaning. However, the wave function squared represents an orbital, which is known as the position probability distribution map of an electron of a given energy. So again, it's saying for an electron of a given energy, here is the probability of an electron being in this location. So the amplitude of the wave function at a given point can be related to the probability of finding the electron at that position. Now, critically, there are also going to be observable regions where the electrons will not be found, called nodes. So we can see this quite dramatically. So if we look at, for example, a probability density diagram as a distance of radius, you may notice that there are regions of zero amplitude in our probability density called a node. What this means is that in our orbital depiction, there will be a region of space. There will be a region of space where there is zero probability of finding an electron. So this region of zero probability is called a node. And in a node, electrons are not present, and there's zero probability of finding an electron at that location. Okay. Now, exact solutions to the Schrodinger equation can only be achieved for one electron atoms. For multi-electron systems, electron energies can only be approximated due to the fact that these electron-electron interactions will adjust and modify your electron energies. Okay, so we're starting to model electrons in terms of probability densities for electrons of a specific defined energy. Okay. So let's talk a little bit about the wave function now in quantum numbers. So the wave function is a function of 4 different quantum numbers. And what's really important is that the energy of an electron can only be solved for a specific set of quantum numbers. So we can only accurately describe the energy of an electron for a specific set of quantum numbers. Now, the square of the wave function, which depends on these quantum numbers, yields the probability of finding an electron relative to the nucleus. The wave function squared is best represented as an orbital, which is the volume of space an electron of a given energy is likely to occupy. And rather than describing the wave function squared mathematically, we often in chemistry like to draw orbital pictures to represent the wave function squared when plotted. So if we were to plot and calculate the wave function squared, we get these orbital pictures. And again, these orbital pictures are representing the probability density for the location of an electron for a specific electron energy. Okay, so for an electron of a given energy, where is that electron likely to be located? Not will it be located, but where is it likely to be located? So somewhere in this region of space, for example, an electron is likely to be found. Does this make sense so far? I find when you start looking at the wave function pictures, it makes things a little more tangible. It really helps you visualize this idea of a probability density or a region of space where an electron is likely to be located. Can I get some responses in the chat? Is everyone somewhat comfortable with this idea? Do orbitals feel a little bit more tangible now that you've seen what these pictures look like in practice? Any questions so far? Don't be shy to type your questions in the chat, and I'll be happy to answer any questions that you have. This is a critical concept necessary not only for this course, but something that will be focused on again in organic chemistry. Okay, so let's delve into orbitals in a little bit more detail, and let's talk a little bit about orbitals. So again, the wave function itself has no physical meaning. we can describe and we can model our probability densities in two major ways. The first of which is the probability density squared, which is the probability of finding an electron at a particular distance and at a particular angle from the nucleus. So if we trace out from our nucleus and we sample a given location at a distance r and a specific angle, this graph is describing the probability of finding the electron at that specific location and specific distance from the nucleus. Another far more common method of describing an orbital and describing the probability density for an electron is the total radial probability, which is the wave function squared total. This is the probability of finding an electron at a particular distance from the nucleus at all angles about the nucleus. So for example, we'd be going off a distance r and then sampling almost like a sphere cutout. And we'll be sampling at the total probability of finding an electron at that distance r. And what these probability densities are describing are the likelihood of finding an electron, and it serves as a proxy for describing the relative amount of electron density at a certain distance from the nucleus. So these orbital pictures can serve as an analog and can serve as a tool to estimate electron density at different positions relative to the nucleus. Of course, these are still probabilities, but they very closely correlate to the empirically observed and the empirically determined electron densities. Okay, so let's talk a little bit about quantum numbers. So the wave function is a function of 4 quantum numbers. Now, we can only determine the energy of an electron for a specific set of quantum numbers. Okay, the square of the wave function yields the probability of finding an electron in relation to the nucleus. This volume of space that electrons are likely to occupy are called orbitals, and orbital pictures are representing the wave function squared. N is one of the main quantum numbers that affects electron energy, orbital energy, and the principal quantum number n in particular controls the energy and size of an orbital. That makes sense. We've seen n before, and n essentially dictates the relative distance of an electron from the nucleus. In other words, the size of an orbital. Now, n must be a whole number. It ranges from 1, 2, all the way to very large whole numbers. The next quantum number in our list is L, which is the angular momentum quantum number. This specifies orbital shape. L ranges anywhere from 0 to n-1. Just to give you a teaser, an L equals 0 orbital is known as an s orbital, and it looks like a sphere. As we move to L equals 1, which is permitted when we have n is equal to 2 or above, L equals 1 is known as a p orbital. And a p orbital is shaped almost like a dumbbell. Does everyone see, as we change L, does everyone see the dramatic change in the orbital shape? Does everyone see how when we changed L, do the shapes look the same or different? Do the shapes look the same or different? different. They clearly look different. So changing L changes your orbital shape. Finally, ML is known as the magnetic quantum number, and the magnetic quantum number specifies orbital orientation. So ML ranges from negative L to positive L. So for example, if we are looking at L is equal to 1, if we're looking at a p orbital, we could have ML values equal to positive 1, 0, and negative 1. And as a result, as I'd like you just to note, what do we see as ML changes? What happens to our orbitals? The shape is the same, but is the 3D orientation of our orbital, is the direction that our orbital is pointing and arranged in space the same or different? Different, exactly. So ML controls the orbital orientation, and you can have values of ML equal to positive L all the way to negative L. Now I like to, and although this is a bit of a heuristic shortcut, I like to think of these first three quantum numbers as describing the orbital, the region of space that the electron is likely to be present in. While this last quantum number, the spin quantum number, focuses in on the specific electron that you are describing. And MS is known as the spin quantum number, and it specifies electron spin. More on this later. Just to give you a heads up, so for a given orbital, we can have two different spin values. Spin value of +1/2 or up spin, and a spin value of -1/2 or down spin. We'll talk more in terms of what spin represents as we do our deep dive into each of these different quantum numbers. So each of these quantum numbers, each unique set of quantum numbers, describes a unique electron with a unique probability density and a discrete defined energy. Let's now look at how each of these quantum numbers affect orbital characteristics, and then we'll look and see how do we define and describe electrons using these quantum numbers. So let's start off with the first major quantum number, which is the principal quantum number n. So we can think about electrons as sorted into principal energy levels, which are dictated by their value of n. This is also called a shell. A shell can be related to the periodic table in that it is a row in the periodic table. So for example, if we look at the second row in the periodic table, this is the n equals 2 shell, while the first row is n equals 1. So all orbitals with the same principal quantum number are found in the same shell. Now n as the principal quantum number dictates orbital size and orbital energy. The larger the n, the larger the orbital. So here we have an n equals 1 orbital compared to an n equals 2 orbital. And my question to all of you is, which orbital is larger? Which orbital is larger? Which electron is farther from the nucleus? The n equals 2. And because the n equals 2 orbital is larger, so larger orbital leads to electrons farther from the nucleus. Ergo, we have higher energy electrons in that orbital. Does that make sense to everyone? We're farther from the nucleus, so as a result, we're less stabilized by our nuclear charge, and as a result, our electrons are higher in energy.
Hey, Professor, I had a question.
Yes.
Does this apply even like following the octet rule?
So the octet rule is describing how we place electrons into orbitals for multi-electron atoms. And the octet rule also is describing bonding, which is the sharing of electrons via orbital overlap. That is a little bit more of a complicated process from an orbital perspective. In bonding, you're actually overlapping and hybridizing orbitals and then overlapping those hybrid orbitals to share electrons and form bonds. So yes, in terms of bonding is done and bonding occurs via the overlap of orbitals. And as we change the n value of the orbitals that we overlap, that has an immediate effect on the nature in terms of energy and in terms of relative bond length of our chemical bond. We'll talk more about how orbitals are used for bonding in the next few chapters. But yes, this idea that the n value of an orbital directly impacts the electron energy and the orbital energy is very critical when it comes to talking about bond energy in terms of bond length and bond strength. Did that answer your question?
Yes, thank you.
Perfect. So when we have a principal energy level n, or a shell, this shell is then divided into subshells with different orbital shapes. And a subshell is known as a section of a row in the periodic table. So let's look at n equals 2 once again. And you may notice that the periodic table is almost conveniently divided into these discretely colored and labeled regions. So this n equals 2 shell is divided into two subshells, the L equals 0 or the S block, which is our first two elements in that row, and then the L equals 1 or the P block subshell, which is the last 6 elements. So in a shell, we have two discrete subshells. And that's because for n equals 2, we're permitted to have L values equal to n minus 1 to 0. In other words, in this case, we have L equals 1 and L is equal to 0 as our two subshells. Now, L is known as the angular momentum quantum number, and the angular momentum quantum number specifies the orbital shape, and L can range anywhere from 0 to n minus 1. So depending on your shell, you have a different number of subshells. To describe the different types of orbitals that result from different L values, the s orbital corresponds to L equals 0, the p orbital corresponds to L is equal to 1, the d orbital corresponds to L is equal to 2, and the f orbital corresponds to L is equal to 3. So your n, your principal quantum number, must be 1 or greater to observe an s orbital. Your n must be greater than or equal to 2 to start observing p orbitals. Your n must be greater than equal to 3 to observe the d orbitals. And your n must be greater than or equal to 4 to observe the f orbitals. Okay, so we only start seeing certain subshells as we move down the periodic table and we get to larger n values. Okay, so let's talk more about each of the orbitals. So the first of which is our s orbital, which corresponds to L is equal to 0. They're spherical shaped, and because they're a sphere, they only have one orbital orientation. ML is equal to 0. So here's what an s orbital looks like. It's a nice, perfectly symmetrical sphere. And if we look at the probability densities, the probability of finding an electron increases as we get closer to the nucleus. Now here's a great time for us to revise and look over again this idea of nodes. Now nodes are a region where a wave has 0 amplitude. Now the amplitude of our wave function is indicating the probability of finding an electron at that specific radial distance or angle. In other words, a node is a region of space that has 0 electron density. And we can calculate nodes by taking the n value minus the L value minus 1. So in this case, if we're looking at a 2s orbital, so let's suppose we're looking at a 2s orbital, which is n is equal to 2, L is equal to 0, our number of nodes would be equal to 2 minus 1, or 1. And as we can clearly see from our probability density diagrams, for our 2s orbital, how many nodes do we see? How many regions of 0 probability of finding an electron do we see? How many nodes do we see? In either our picture or our graphical representation, how many nodes, how many regions of 0 electron density do we see? And don't be shy to submit your responses in the chat or to unmute and state your answer verbally. 1, yep, we have 1 node. Does everyone see this one region with no electron density that's not shaded in? And graphically, does everyone see the region where our probability goes to 0? That is known as a node. As we increase our n value and we look, for example, at a 3s orbital, our number of nodes, so for 3s, we have n is equal to 3, L is 0. Our number of nodes is equal to 3 minus 1, which is equal to 2. And as we can see, for our larger 3s orbital, how many nodes do we have? How many nodes do we see? For a 3s orbital, how many regions of 0 probability density for our electron do we see? And don't be shy, it's not a trick question. How many nodes do we see? For our 3s orbital, we see 2 nodes. Exactly right. Okay, perfect. Nodes are really important to understand when we start to look at how orbitals interact, whether we observe constructive, destructive, or no interaction whatsoever during an orbital overlap. Okay, so let's look now at our p orbitals. These correspond to L equals 1. They're dumbbell shaped. And because our L is equal to 1, we have 3 allowed ML values, remembering that ML ranges from negative L to 0 to positive L. We have 3 different spatial orientations. And as a result, we have 3 unique p orbitals. If you look at the probability density, this time we're looking at radial probability for a p orbital, we see that there is a node. Does everyone see that node in the center of our p orbital? Does everyone see this region of space where no electrons are present? Does everyone see that node in the middle of our p orbital? We have a region in the center of our p orbital with 0 probability of finding an electron. And as we can see from our radial probability picture, as we move away from the nucleus, our probability increases and then it drops off as we get farther and farther away from our nucleus. But at our nucleus, the radial probability is 0. Now, just as a side note, if you're drawing a p orbital, p orbitals are phased. Just like a wave has regions of positive and negative amplitude, our p orbital has regions of positive and negative amplitude. So I'd like, especially as you'll be using this idea in organic, and when we talk about orbital overlaps, this is going to be critically important. I'd like that you draw your p orbitals with one lobe shaded to showcase this idea of phasing. And that represents one portion of the p orbital is positively phased, not charge, phase. Well, one region has a negative phase, not charge, phase. This will be important later on, so I'm just laying this groundwork now. Now looking at the d orbitals, things get a little funny. We have L is equal to 2. These orbitals are clover shaped. And because we have L is equal to 2, we have ML values from negative L to 0 to positive L. So we have 5 different spatial orientations. And as a result, we have 5 unique d orbitals. Okay. This will be important in a moment. Right now, we're just starting to understand what do these orbitals look like, how many orbitals are found in each subshell, how many unique orbitals do we have for each L value, and are there any unique characteristics in terms of how the orbitals are phased. Okay, lastly, the f orbitals correspond to L is equal to 3. We don't typically see the f orbitals as those elements that have f orbitals that actively participate in chemical bonding are pretty far down in the periodic table. But just for completeness, we have 7 unique f orbitals with 7 unique orientations. Okay. So now what we're going to do is we're going to talk a little bit about each of the quantum numbers, and we're going to talk about how the different quantum numbers are related. So we know that we have n, which is the principal quantum number, which indicates the energy and size of an orbital. We can have whole number values of n starting from 1 and going to very large whole numbers. L is the angular momentum quantum number, which specifies orbital shape, and L can go from 0 to n-1. ML is the magnetic quantum number, which specifies orbital orientation, how the orbital is arranged in 3D space. The spin quantum number we'll leave for a later discussion, but let's now talk about how these 3 quantum numbers are related to each other. So how are N, L, and ML related? So we can think first and foremost of sorting each of our orbital sets into shells. So we have n equals 1, n equals 2, and n equals 3. Each of those shells can be further divided into subshells, where L is equal to n minus 1 all the way to 0. So in this case, we have the L equals 0 subshell. For n equals 2, we can access L is equal to 1 and L is equal to 0, or S and P orbitals. For n is equal to 3, we can access L equals 0, which is S, L equals 1, which is P, and L equals 2, which are the D orbitals. Each of those subshells contain a unique number of orbitals based on the ML values. So for example, the S orbital has 1 ML value, so we see 1 orbital. The p orbitals, on the other hand, have 3 ml values, and as a result, we observe 3 unique orbitals. So we have 3 p orbitals. Okay, so we start with our shell, then we look at our subshell, and then finally we look at the ml value to fully describe the exact orbital that is being used to describe our electron. Remembering that n dictates what numbers of L are allowed, which dictates what numbers of ML are allowed. So let's do a little bit of a comprehensive check, and let's try to designate each of the orbitals below as allowed or invalid. So let's take a look at this list. So 1s, that's n is equal to 1, L is equal to 0. That is okay. A 1p orbital, that corresponds to n equals 1, L equals 1. Is that allowed? N equals 1, L equals 1. Is that allowed? Yes or no? If we know L, we can have n minus 1 all the way to 0. Can we have n equals 1 and L equals 1? Is that allowed? Yes or no? No, it's not allowed. So let's cross it out. A 1D, that's n equals 1, L equals 2. If L is equal to n minus 1 to 0, is a 1D orbital allowed? Is a 1D orbital allowed? No. So let's cross it out. A 2D orbital, we have n equals 2, L is equals to 2. If L is equal to n minus 1 all the way to 0, is a 2D orbital allowed? Is a 2D orbital allowed? No, it's not. So let's cross it out. Finally, a 3s orbital, which is n equals 3, L equals 0. If L can count from n minus 1 all the way to 0, is a 3s orbital allowed? Is a 3s orbital allowed? Yes, it is. Perfect. So now what I want us to do is to look at the following set of orbitals and describe each of the orbitals as allowed or invalid. And we'll discuss this example in about 3 to 4 minutes. And don't be shy to share your responses for any of these 5 orbital depictions in the chat. And we'll discuss this example in another 2 to 3 minutes. And the responses I see in the chat look good so far. One thing I would consider is that you can have n, as long if your n value is greater than L, your orbital is likely to exist and likely to be not exist, but likely to be allowed would be a better way of putting it. But overall, the responses I see in the chat look great. Let's try to get a few more responses. And then we'll discuss in about another minute and a half. Okay, so let's discuss this example. So 3f, that corresponds to n is equal to 3, L is equal to 3, is a 3f orbital allowed? Is a 3f orbital allowed? No, it's not. So we cross it out. Okay. What about a 4f orbital? That's n equals 4, L is equal to 3. If L can range from n minus 1 all the way to 0, is a 4f orbital allowed? Yes, perfect. For a 2p orbital, that's n equals 2, L equals 1, is a 2p orbital allowed? Yes. Okay, for a 10d orbital, we have n equals 10, L equals 2. Is this 10d orbital allowed? So if L can be equal to n minus 1 and any value in between counting to 0, is a 10d orbital allowed? Is 2 less than 10? Yes. So then a 10d orbital is certainly permitted, although a bit strange. Finally, for a 1f orbital, we have n equals 1, L is equal to 3. Is a 1f orbital allowed? is a 1f orbital allowed?
No.
Yep, so we cross it out. Perfect, perfect. Okay. So let's keep going now and let's talk a little bit about the electrons in orbitals. So we can think of an electron sort of like a tiny magnet that interacts with an external magnetic field in one of two ways. The tiny magnet will either be quote unquote spinning. Now, the electrons aren't actually spinning, but when a charge rotates or spins, it generates a magnetic field. And electrons themselves generate a tiny magnetic field. And it can be either modeled as an upspin or a downspin magnetic field. So spin is describing the field produced by an electron. It can either be upspin or downspin. And the spin quantum number specifies electron spin, which is the magnetic field produced by your electron. MS, we only have two values. We can either be plus 1/2 or minus 1/2. Now, a key feature of opposite spins is that opposite spins will form what's known as a pair in an orbital. Opposite spins like to pair. Now, the reason why this is important is following what's known as the Pauli exclusion principle, no two electrons in the same atom can have identical values for all four quantum numbers. So electrons can only occupy the same orbital, which has the same n, l, and ml value, only if the electrons have opposite spins that are paired. So we have two electrons of opposite spins in an orbital. So for example, if we were depicting an orbital with a box, we'd draw our up spin electron with an up arrow and our down spin electron with a down arrow. So the up spin has ms of plus 1/2, the down spin has ms of minus 1/2. So we can fit two electrons in an orbital if they have opposite spins. We can't have two electrons with the same spin in the same orbital because all of their quantum numbers would be the same, and in turn that would mean we're essentially describing the same electron. Now, if all of our spins are paired, we call those compounds or species diamagnetic. Substances with more spins in one direction that contain unpaired electrons are known as paramagnetic substances. So for example, if we have an unpaired electron, this is known as a paramagnetic species. Now you may say, why should I care about diamagnetic versus paramagnetic? Well, if you've ever seen these signs associated near an MRI machine, or if you've ever been to the doctor's office, before you go in for an MRI, you have to take off jewelry and other metals. It's also the same reason why you can't bring certain wrenches near an MRI. It's because those pieces of metal have an excess of unpaired electron, or they have an excess of electrons with one defined spin. And as a result, when you bring this paramagnetic substance or species into a magnetic field, it gets attracted to the magnetic field. And this is how you end up with people getting stuck with their hand pinned to an MRI machine because they tried to move a heavy object made of copper near the MRI. So this is a relationship between this very sort of micro scale property, whether or not our electrons are completely spin paired or whether we have unpaired electrons, and a macro scale observation. The person who is carrying this oxygen tank is now stuck to the MRI machine or pinned to the MRI machine. Does that make sense to everyone? This idea of spin, upspin and downspin, and diamagnetic versus paramagnetic. So in order for us to have two electrons in an orbital, they must have opposite spin values, opposite spin quantum numbers. Okay, so we can actually also see this phenomena of electron spin if we look at the Stern-Gerlach experiment, where a beam of silver atoms were ejected through a magnetic field, and what we observe is that only discrete deflections are observed based on the electron spin in silver atoms. So we see this very clear deflection of our silver atoms based on the electron spin of electrons in our silver atoms as they align or repel relative to the magnetic field. Also, if you are paying close attention to our description and our observation for the emission spectrum of hydrogen, what we see in many emission spectra are the appearance of what are known as doublets. And these doublets are the result of electrons with identical NL, ML values and identical energies, but different MS or spin values. That's why we see two emission lines, one for our MS of +1/2 electron, the other for our MS of -1/2 electron. That's why we see these doublets, because we have two unique electrons with two different spin quantum numbers. Does this make sense to everyone so far? This idea of the spin quantum number? All four of our quantum numbers are used to describe a unique electron. Different electrons have a different set of quantum numbers, and if they have the same energy but a different spin quantum number, we have two electrons with the same energy but we have two different electrons with that same energy. Any questions on this example? Does this make sense to everyone so far? Okay, so let's now talk a little bit about how our orbitals filled with electrons. So each electron in an orbital has a unique set of quantum numbers, N, L, ML, and MS. So N is our principal quantum number. It indicates the energy and size of an orbital, or the energy of an electron and how far away that electron is from the nucleus. It has whole numbers that range from 1, 2 to very large numbers. L is the angular momentum quantum number, which specifies orbital shape. L can range from 0 to n-1. ML is the magnetic quantum number, which describes the specific orbital orientation, and ML ranges from -L to 0 to +L. And finally, we have MS, which describes specifically the electron spin, or the spin of the electron that's in that specific orbital or described by that specific orbital. And the spin value can be either +1/2 or -1/2. Now, critically, when we think about filling orbital diagrams, electrons occupy the lowest energy orbitals first, then the higher energy orbitals are filled. For each orbital, for an N, L, and ML value, you have two possible spin quantum number values. Thus, each orbital can hold a maximum of 2 electrons of opposite spins, and that's the maximum limit. There can be less electrons in a given orbital. So for example, a 2s orbital can hold 2 electrons, an upspin electron and a downspin electron, where each of these arrows represent 1 electron, and up represents upspin, down represents downspin. The reason for that is that we can have a total of 2 unique sets of quantum numbers which describe 2 unique electrons in our 2s orbital. Does that make sense to everyone? So key takeaway, each orbital can hold 2 electrons, 1 upspin, 1 downspin. Does that make sense to everyone so far? Okay, so let's try to answer some questions. The first of which, how many electrons can we have in a subshell? So let's just qualitatively get a sense of how many electrons are found in a subshell, where a subshell, just as a reminder, is a region or section of a row in the periodic table. Now this is where things are going to get really cool if you're looking at your periodic table. So first, we're going to count the number of orbitals for the subshell L. So let's look for L equals 0, for example, which is our s orbital. We have ML values equal to 0. So we have 1 orbital. Okay. And we know, okay, so that's our first step. For L equals 1, which is our p orbital, we have ML values equal to +1, 0 to -1. So we have a total of 3 orbitals. Okay. For L equals 2, which is our d orbitals, I'd like you to tell me in the chat, how many ML values can we have? How many unique ML values can we have? How many unique ML values can we have? So we have -2, -1, 0, +1, and +2. So how many total ML values do we have? How many total unique orbitals? We have 5 unique orbitals. I'm just going to draw out a few of them. Okay, each orbital can hold 2 electrons. So to figure out the total number of electrons in a subshell, we're going to multiply the total number of orbitals by 2 to get the number of electrons per subshell. So for L equals 0, which is our s orbital, we have ML is equal to 0. We have 1 orbital times 2 electrons per orbital. And that in turn gives us, for our s orbital, we can have a total of 2 electrons in our s subshell. And as we notice in the periodic table, for example, in the n equals 3 shell, we have 2 elements at the start, which are known as the quote unquote S block elements, which are our first 2 elements. So does everyone notice how in the periodic table you see on the left-hand side a set of 2 elements at the start? That is known as our S block. Now let's look at L is equal to 1, which is our P block. We have ML values ranging from -1 to 0 to +1. And yes, there is a reason I'm setting this up exactly in this orientation. So we have 3 ML values. So we have 3 orbitals times 2 electrons per orbital. That gives us a total of 6 electrons. So let's draw out a picture of that. Now you may notice that on the far right of the periodic table, you'll notice a block of 6 elements. And this block of 6 elements is known as the quote unquote P block. So we're slowly starting to see this connection between the organization of the periodic table in terms of reactivity, as well as the organization of the periodic table in terms of electron configuration, shells, and subshells. Finally, for L is equal to 2, we have the D block, which has ML values of -2, -1, 0, +1, and +2. So we have 5 orbitals, and we have 2 electrons per orbital. That in turn gives us 10 electrons. So for our D block, we have 10 electrons, and that is why you see in the middle of the periodic table a block of 10 elements in the middle of our periodic table, and these are known as the D block. This also explains why the D block appears at the 3rd row and below, because L equals 2 is only allowed when we have N equals 3 or greater. So we're really starting to see a connection between the arrangement of elements in the periodic table and the different shells and subshells associated with electron configurations and orbital models of an electron. So in summary, what I want you to take away, the s orbital holds 2 electrons, the d orbital 10, p orbitals in total hold 6. Okay, so now that we have that set up, let's talk about how many electrons are found in an energy level or a shell. So what we're going to do first, we're going to determine the number of subshells. We're going to count the number of orbitals in each subshell. We're going to then multiply by 2 to get the total number of electrons, and then we're going to add the electrons in each subshell together. So let's look at n is equal to 1, or the first row in the periodic table. We have L values allowed of L is equal to 0. That gives us an ML value equal to 0. So we have 1 orbital times 2 electrons per orbital gives us 2 electrons. That's why in the first row of our periodic table, we have a total of 2 elements. Pretty cool, right? So for n is equal to 2, we have L is equal to 1 and L is equal to 0. So we have our P and S blocks. That gives us ml of 1, 0, and -1, and ml of 0. So we have a total of 3 orbitals in our P block times 2. We have 1 orbital in our S block times 2. That in total gives us 6 electrons plus 2 electrons, or 8 electrons total. This is very closely related to the reasoning and sort of logic behind the octet rule. 8 electrons constitutes a full valence shell for most elements. And that is why, if we look at the second row in the periodic table, if you take out your periodic table, without me drawing it, just looking at your periodic table, how many total elements do we see in the second row? How many total elements do we see in the second row? If looking at the periodic table, how many elements do we see in the second row? Just counting. Taking out your copy of the periodic table, how many elements do we see? 8, exactly right. So if we look at the second row of the periodic table, we see a total of 8 elements. Because we have 8 electrons total in our second shell. Okay, so let's look at n equals 3. Here we have L is equal to 0, L is equal to 1, and L is equal to 2. That gives us ML values of 0 for L equals 0, ML values of -1, 0, and +1 for L equals 1, and ML values of -2, -1, 0, +1, and +2 for L is equal to 2. Okay, so now that we have this set up, we see we have 1 orbital in our S block times 2 gives us 2 electrons. We have 3 orbitals in our P block times 2 gives us 6 electrons. In our D block, we have 5 orbitals times 2, which gives us 10 electrons. If we add this together, we get 18 electrons total in our n equals 3 shell. Does this make sense to everyone so far? Calculating the number of electrons found in a given shell and subshell. This will be useful to remember when we talk about electron configurations. Okay, so let's keep going now. What I want you to do is, given the following set of quantum numbers, I'd like you to indicate the orbital that an electron would be present in for the following quantum numbers. So I'll do the first example. So for n equals 2, L equals 1. So we have a 2p orbital and we have an upspin electron. So we have a 2p orbital and we have an electron with an upspin. I'd like you now to attempt the following 2 examples. I'd like you to describe the orbital that an electron is present in for the following set of 2 quantum numbers. and then I'd like you to tell me whether the electron is upspin or downspin. And we'll discuss this example in about 2 to 3 minutes. And we'll discuss this example in about 1.5 to 2 minutes. And don't be shy to message me in the chat with your proposed response for each of these 2 sets of quantum numbers. And I'd like to see a few responses in the chat before we discuss. And we'll discuss this example in another minute. For the first one, the response I see is perfectly correct. Yep. Yep, exactly right. And the second response I see looks exactly right. Perfect. Spin would be downspin. Let's talk about this example. So for the first case, we have n equals 4, which is a 4. L equals 2 is a p or L equals 2 is a d orbital. So we have our 4d orbital, and ms of plus 1/2, we have an upspin electron. In the second example, L equals 1, so we have 1. N equals 1, so we have 1. L equals 0, that's an s orbital. So we have a 1s orbital. And since our spin value is minus 1/2, we have a downspin electron. Perfect. So we're beginning to correlate the set of quantum numbers with the exact orbital, energy, and spin value of our electron. Wonderful. Any questions on this example? If not, let's keep going and let's talk, and this is where we'll leave off on this chapter. So let's talk about the distinction between single electron atoms and multi-electron atoms. So for single electron atoms, each electron in an orbital has a unique set of quantum numbers to describe that electron. Each orbital can hold 2 electrons of opposite spins, and the energy for an orbital with the same n and L value are degenerate. So for a single electron atom, for the same n value, we have the same orbital energy. Okay, wonderful. Now, I'd like you to compare. Here's our picture for a single electron atom. Here's our picture of orbital energy as a function of n. When we look at a multi-electron atom, we suddenly see a dependence where our orbital energy depends on n and L. And that is because electron-electron repulsive interactions directly affect your orbital energy. So, this is where we're going to leave off this chapter. And what we're going to do next session is we're going to delve into chapter 11, where we look at multi-electron atoms, writing out full electron configurations describing how the electrons are arranged in multi-electron atoms. And then finally, we're going to use electron configurations and orbital and electron energies to explain periodic trends such as ionization and reactivity. So this is a great stopping point for today, as this leads in to our next lecture on chapter 11. So I'm going to pause and stop this recording.